We start this lecture with an overview, a plan for what will be presented. In this pre-lecture, we will begin our study of fluids. We will start with a discussion of the origins of pressure in a contained fluid. We will use Newton's second law to determine the relationship between this pressure and the depth below the surface of the fluid. We will then use this relationship to obtain Archimedes' principle, the relation between the buoyant force on an object and the volume it displaces when placed in a fluid. Finally, we will examine the conditions for sinking and floating, including a determination of the submerged fraction of a floating object. So far in this course, we have focused on systems involving solid objects, boxes, cylinders, springs, and ramps, for example. We know that ordinary matter can also exist as liquids and gases, and we will devote the last two pre-lectures of this course to understanding the similarities and the differences between the three states of matter in the context of the central ideas in the course, namely forces and motion. Our picture of the atoms that make up a solid object is that they are more or less rigidly fixed in position relative to each other. Applying a force at one point on a solid object will cause the object to move as a whole according to Newton's laws. The shape of the object stays the same unless it is somehow bent or broken. In a liquid or a gas, the positions of the molecules are not fixed. They can move relative to one another and assume a shape determined by their immediate environment. The molecules in a liquid bind weakly with each other in such a way that they are about as close together as they can get, even though their positions are not fixed. The molecules in a gas do not bind with each other at all and tend to be much further apart. Despite these differences, many of the concepts that we will develop in the next two pre-lectures will be identical for liquids and for gases. Indeed, the fact that neither of these are rigid means that we will need to re-examine the way we describe both forces and motion in problems involving these states of matter. We will start this discussion by introducing the concept of pressure on the next slide. Here we see a glass of water sitting on a table. The weight of the water causes the liquid to push outward on the inner surface of the glass, and the glass in turn keeps the water from spilling by pushing back inward on the liquid. These forces balance, and the system is in static equilibrium. Even though the overall situation seems pretty simple, we need a better way to describe the forces involved before we can quantify them. The origin of the macroscopic force between the liquid and the wall is the collisions between the individual molecules of the liquid and the wall of the container. Each time a molecule collides with the wall, its momentum changes in a direction perpendicular to the wall. Therefore, during the collision, there must have been a perpendicular force exerted by the wall on the molecule to cause its change in momentum. Since we are interested only in macroscopic properties, we will account for these collisions by determining the average force acting over a time interval. We will then define the pressure as this average force per unit area on the wall. For example, if the average force of the water in a pool pushing against an underwater window is 10,000 newtons, and the area of the window is 2 square meters, then the pressure of the water on the window is 5,000 newtons per square meter. The same pressure acting on a window having twice the area would exert a total force on the window that was twice as big. The pressure of a liquid always produces a force that is perpendicular to the surface it touches. Molecules making up a liquid will collide with any object, even each other, in exactly the same way that they collide with the walls of their container. Therefore, pressure is a concept that has meaning everywhere in the liquid, not just where it touches the container. For example, you can feel the pressure in your ears increasing as you dive to the bottom of a swimming pool. Indeed, we will discuss this change in pressure versus the depth in a liquid on the next slide. Here we see a tank containing some liquid. Our task is to determine how the pressure in the liquid varies with the depth beneath the surface. Since the liquid in the tank isn't going anywhere on average, the net force on it must be zero. For the same reason, the net force on any part of the liquid we choose to focus on must also be zero. Here we see a small volume of the liquid inside the tank. The volume is a cube whose sides have height h. Since the liquid is identical inside and outside the volume, the net force on the volume must be zero. What forces act on this volume? Well, the weight of the volume, which can be determined from the density of the liquid and the volume of the cube, points down. The pressure of the liquid will exert a force on all 6 sides of the cube, but since these forces are always perpendicular to the sides, only the pressure acting on top and bottom surfaces will result in vertical forces. We can now use the fact that the net vertical force on the cube must be zero to find a simple relationship between the pressure difference between the top and the bottom of the cube. Namely, the difference in pressure is simply proportional to the difference in depth. This result has 2 important features. First, it demonstrates that any 2 points at the same depth have to have the same pressure. Second, it defines the quantitative dependence of the pressure in the liquid on the depth. We will use both of these features on the next slide when we work through the example of measuring atmospheric pressure. Here we see a long transparent tube submerged in a swimming pool. Its top is sealed so that there is no air inside it. The sealed end of the tube is now raised out of the pool, and the water inside the tube rises with it, just like it does if you cover the end of a straw as you pull it out of a glass of water. As the tube is pulled upward, a height is reached after which the level of the water in the tube stays constant as the tube is raised. Why does this happen? We just learned how pressure varies with the depth in a given liquid. We can use this knowledge to compare the pressure at the surface of the pool with the pressure at the top of the column of water when it is at its maximum height. Since the surface of the water in the pool is stationary, the pressure just beneath the surface must be the same as the pressure just above the surface. This pressure just above the surface is the atmospheric pressure, typically about 10 to the 5th newtons per square meter, or about 15 pounds per square inch. Now, we know that the pressure in the liquid is determined by the depth. Therefore, the pressure at a point inside the tube, which is at the same height as the surface of the water just outside the tube, must also be equal to the atmospheric pressure. Since there was no air in the top of the tube to begin with, the space that opens up above the water as the tube is raised contains no air at all. And the pressure there must just be the vapor pressure of the water, which is so much smaller than the outside atmospheric pressure that we can call it zero. Therefore, the difference in pressure at the water's surface and at the maximum height of the water in the tube must just be equal to the atmospheric pressure. This height, then, can be used to actually measure the atmospheric pressure. Such a device is called a barometer. Most barometers of this design use mercury rather than water, since the density of mercury is much larger, almost 14 times larger, than that of water, so that the heights involved are smaller. For example, typical atmospheric pressure, 15 pounds per square inch, corresponds to a height of about 29 inches of mercury, a phrase you've likely heard in weather forecasts. Buoyancy is the upward force that an object experiences when it is placed in a liquid. This force determines whether an object floats or sinks when it is put in a liquid. The buoyant force can be understood in terms of the ideas we use to derive the depth dependence of the pressure in a liquid. Namely, since the total force on any particular volume of the liquid must be zero, we determine that the net upward force due to the pressure of the liquid surrounding it, that is, the buoyant force, is just equal to the weight of the liquid in the volume. we say the buoyant force on any object placed in a liquid is just equal to the weight of the liquid displaced by that object, which is known as Archimedes' principle. We now replace this volume of liquid with an equal volume of another material that has a greater density than the liquid, say steel. What will be the buoyant force on this object? Well, it must just be the same as the buoyant force on the previous volume of the liquid, since the force is just determined by the surrounding liquid, which has not changed. In this case, since the density of the material is greater than that of the liquid, the buoyant force will be less than the weight of the object, and it will sink to the bottom of the tank. The force needed to lift the object off the bottom of the tank, however, is now less than the weight of the object, since the buoyant force is always present and always points up. In other words, if we suspend the object from a string while it is submerged in the liquid, we will again have a case of static equilibrium, and the tension in the string will be less than the weight of the box by an amount exactly equal to the buoyant force. On the last slide, we introduced the buoyant force and examined an example of this force exerted on an object whose density was greater than that of the liquid. What happens if we replace that object by another one whose density is less than that of the liquid, say a plastic box? We start by completely submerging such a box in the liquid. The weight of the box is now less than the weight of the displaced liquid, hence the net force on the box points upward, causing it to rise. Once it reaches the surface, it will simply float. Since the box is motionless, once it floats on the surface, it must be in static equilibrium. Therefore, the net force on the box must be zero. In particular, the upward buoyant force on the box due to the liquid must be exactly equal to the downward weight of the box. We already know that the buoyant force is equal to the weight of the displaced liquid. Therefore, an object that floats must be displacing exactly its own weight of the liquid. Since the density of the liquid in this case is greater than the density of the box, only part of the box will be under the surface of the water. To determine exactly how much of the box will be below the surface of the water, we just need to set the entire weight of the box equal to the weight of the liquid displaced, which is simply proportional to the product of the density of the liquid and the submerged volume of the box. Thus we see that the submerged fraction of the box just depends on the relative densities of the box and the liquid. The closer the density of the box is to the density of the liquid, the bigger the submerged fraction of the box. For example, a piece of styrofoam, which is much less dense than water, will float with very little of its volume submerged. On the other hand, an iceberg, which has a density that is about 90% that of water, will have about 90% of its volume submerged as it floats. We conclude with a brief discussion of the main points of this pre-lecture. First, we define the pressure in a fluid as the average force per unit area exerted by the molecules of the fluid during their collisions with the container walls. The molecules that make up the fluid will collide with other molecules in the fluid in exactly the same way, so that the pressure is a concept that has meaning everywhere in the fluid. By setting the net force on any volume of fluid in the container equal to zero, we obtain the result that the difference in pressure between 2 points in the fluid is proportional to the vertical distance between the 2 points. Second, we applied this relationship between pressure and depth to determine the buoyant force that the fluid exerts on any object placed in it. In particular, we derived Archimedes' principle that the buoyant force exerted on an object is equal to the weight of the fluid that it displaces. Third, we used Archimedes' principle to determine that the submerged fraction of a floating object is equal to the ratio of the mass density of the object to the mass density of the fluid.